So today we're going to cover the first day of section 6.1, and 6.1 will cover the properties of exponents. So what's important for our work today is just reminding ourselves of what an exponent is. So we know exponents are used to represent repeated multiplication. And there's two important things or vocabulary words that we need to know when we're working with exponential expressions. It's the base and the exponent. Maybe I'll highlight those in blue and red. So you can see the word here, base. We can see the word here, exponent. So the base is the number that we multiply by itself, and the exponent represents how many times we're going to multiply that. So on your notes, if we add this little example down here, 2 to the 4th, so what we would see here is 2 is the base, so we labeled that as the base, and then the 4 obviously is the exponent. So just recognizing where those are and what language we use to talk about them. So when we're working with exponential expressions, what's going to be really important is that you're able to do two things. You should be able to write the expression as a complete sentence, and you should also be ready to expand it, or in other words, write it out as a multiplication problem. So again, let's go back to 2 to the 4th, and let's see what that would look like here. So 2 to the 4th, so the base is the number that we're multiplying over and over, and the exponent is how many times we're going to multiply it. So as a sentence, this means 2, because that's the base, multiplied by itself 4 times. And that sentence stem is something you could use whenever I ask you to write an exponential expression as a sentence. This number here was the base, and this number over here was the exponent. So then when we have to write it in expanded form, I'm a big fan of using boxes. So if the exponent is 4, so I put the number of boxes is the exponent. So if there was the exponent of 4, I'm going to write 4 boxes. And then because it's an exponent, they're all connected by multiplication. And then the base goes in each box. I like that language. So I'd put a 2 there, a 2 there, a 2 there, and a 2 there. So then I can see that, and I could just go back and write it as 2 times 2 times 2 times 2. Either one would be fine. So again, just really quickly making sure that you can write an exponential expression as a sentence, and then also write it out as a complete multiplication problem. But we're actually getting into today, aside from knowing what exponents are, is we're going to look at what's called properties of exponents. And I just want you to think of properties of exponents as rules that we use to simplify expressions that have exponents in it. So for example, if you added this to your notes, if we saw something like 3 squared times x to the 9th times x to the 11th times x to the negative 2, all divided by x to the negative 1, and I'm just making this up. We would want to make that look way simpler. And what our properties of exponents will do will help us to write this in a much more simple way. And what that would mean to us is things like evaluating all the known exponents. Like, I know what 3 squared is. Let's just write that as 9. Another thing it will help us do is get rid of negative exponents. Like I see here, we have a negative 1 and a negative 2, and we'll see what those mean later, but we don't want that in our final answer. And the last thing we want to do when we're simplifying is we only want to write each base once. And what I mean by that is, why do I need to write x times itself so many times? Why couldn't I just simplify all those x's to be how many? 17 of them. So again, we'll get to that, but like, this is way more simplified than it started. So that's what the properties of exponents are going to help us do. And as we're going through the properties of the exponents, make sure that you can do these 5 things with them. Each of them is going to be really important. So let's look at our first property. So here we have the power of a product property. So if 2 of the same bases are being multiplied, we add their exponents and keep the base the same. So in symbols, what you'll need to add to your notes, like if I took some number, a, to a power of m, and it was multiplied by a to some other power, the answer would just be that number a to this new power where I add them. So again, we're noticing that the bases have to be the same. So for example, here, I see 5. Now what I'm thinking about is what I have over here in the margin. What you're asking yourself when we're doing the properties of exponents here is, how many times is 5 actually going to be multiplied by itself? Or in other words, if I had to write this out, how many times would I have to write the number 5? So we're going to expand a little bit here. So what we'd see here is, if I had to write this would be 5 times itself twice. And then here, because the exponent is 3, there'd be 3 boxes, and I'd put 5 in it. So in other words, how many times did I just write 5 in a box? Well, there's 1, 2, 3, 4, 5. So this would be 5 to the 5th. And what we're seeing here is if we use that rule, because this base is the same as that base, that'll be the base of our answer. And then the exponent, what our rule says to do with those exponents, is to simply add them. So I would take 2 and 3, and I would add them. So 2 plus 3 is 5. So again, let's go down and do this one, which you'll probably have to add your notes if it's missing. Let's just think about it in the expanded form first. If I had to write this, since the exponent is 2, I'd write 2 boxes, and in each of those boxes I would put an x. For this one, since the exponent is 5, I'd put 5 boxes, and I would connect them with multiplication, and in each box I would put an x. So what I'm asking myself then is how many times did I just write x multiplied by itself? Right, so x is in each box, and I wrote it 7 times. Now, if we use the rule, what the rule is asking us to see is that if we have the same bases on the exponents, so like here, x is the same thing as x, so our answer had an exponent of x, and then to get the, base of x, to get the exponents, it says to take the current exponents like 2 and 5 and add those together. And we all know that 2 plus 5 is equal to 7. Now with this example, what we're seeing here is we have the same base. So the base, the same thing that has an exponent, is -3 and -3. And if it doesn't have the exponent, we can go ahead and put a 1 there. So if we're using the rule, if I see the same base, that's going to be the base of my answer. And then I can take their exponents and add them together. So this would be -3 to the 3rd power. Or again, if we need to, we could write our boxes. So here I'd have to put 2 boxes for the first one, put -3 in it. And then because that exponent is 1, I'd put 1 box and fill it with -3. So I can see that I wrote -3 3 times. So either way we do it. Now here, this is why we use the rule. If I notice that A is being multiplied by A, their answer would be A for the base. And then to get the exponent, all I would need to do is add the current exponent. So 90 plus 15 is 105. And that's where we'd want to use the rules. If I had to ask myself this question, if I had to write that out in expanded form, how many times would I have to write the exponent of A, or the base of A? Well, here I'd write it 90 times, and here I'd write it 15 times. So I would write A 105 times, and it's all being multiplied. So again, we can always just think about what we would be doing to get the same answer. So that is our power of a product property. Now here we have a 0 exponent property, and in words, any number except 0 to the 0 power is 1. So for example, what you'll need to add, if I took a number like A and I raised it to the 0 power, A to the 0 power is going to be 1. Now it's really important to see why that happens. So we're going to use this little table here. Now in this table, we know that 2 to the first power is just 2. We know that 2 to the second power is 4. We know 2 to the third power is 8, right? And 2 to the fourth power, 2 times 2 times 2 times 2 is 16. So I see this pattern. When I'm going down the table, I'm just multiplying by 2 to get to the next number. So the next number must be 32. And that would be true if we're following our pattern, right? 2 to the 5th power is equal to 32. If I wrote that all out, 2 times 2 times 2 times 2 times 2, that would equal 32. So what I'd ask us to see then, if we're going down the table, we're always multiplying by 2. So if we're going backwards through the table, it looks like we're always dividing by 2. Right, 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. So if we were completing the pattern, 2 divided by 2, there's no other choice but for this to be a 1 because it follows the pattern. So the examples that we'll do today are really straightforward with the 0. If I see a number to the 0 power, it's equal to 1. So here I see 6.5 to the 0 power, so that's equal to 1. Even if the numbers are weird, like pi to the 0 power is 1. You have no idea what the log of 10.79 is, but it doesn't matter because as long as it's to the 0 power, it's 1. So the 0 power property, pretty easy to remember. Any number to the 0 power is 1. So here our negative exponent property. We're actually going to come back here and just complete the pattern here. So if I continue to look at this, if I know the pattern going backwards is dividing by 2, I could just keep going. So 1 divided by 2, that's 1/2. If I kept going, do the pattern again, divided by 2, 1/2 divided by 2 is 1/4. Now if I complete the pattern on the left, so our exponents going this way are getting smaller, right? 5, 4, 3, 2, 1, 0. This exponent must be to the -1, and this exponent must be to the -2. So we're starting to see here is that negative exponents are a thing that exist. And well, how would I get 1/4? Well, I'd ask us to see that this is 1 over 2 squared. This is just 1 over 2. So if I continue the pattern one more time, 2 to the -3, or in other words, if I divided by 2, I would get 1/8. Or in other words, that's 1 over 2 to the 3rd power. So we see this negative exponent thing is something that exists for us to work with. So our rule for negative exponents is a negative exponent to us is actually going to be an action. What it's going to do is going to tell us to move the location of the base, meaning if it's in the numerator, it should go to the denominator. And if it's in the denominator, it should go to the numerator. And then after we move that base, after we complete that action, what's really important to remember is that the exponent then becomes positive. We'll come back. Let's write our symbols right now. So what that means here is if I had something like a to the -3rd power over 1. Right now, a is in the numerator. So if it's in the numerator, the negative exponent would tell it to move the base to the denominator, and then the exponent becomes positive. Now, if I remove everything from the top, I just do a placeholder of 1. Another example that it asks us to see, if I had something like 9 over a to the -4th, right now a is in the denominator of a fraction, so the negative exponent tells me to move it to the top and change it to a positive. Now there already was a 9 there, and as a reminder, when we're working with exponents, it's all multiplication. So if the 9 was already on top, they're being multiplied together. And as we remember before, if we remove everything from the numerator to denominator, we replace it with a 1. So let's look at a few quick examples. And here I have this as a note here, but if I look at number 4, or the number 4, it's not written as a fraction, so I can always divide it by 1 if you need to. So right now the 4 was in the numerator, so it should go to the denominator, and then we should change the negative to a positive, and if we move it on top, we replace it with a 1. And we'll start to simplify these now. Like 4 squared, that's just 16. So here, this 5 to the -9th was in the denominator, so it should go to the top, and it changes to a positive. If I remove everything from the bottom, I replace it with a 1, and then we can just simplify. We don't need to divide by 1. So here, x to the -3rd isn't a fraction, so I'll make it a fraction. So then that x to the 3rd would go to the denominator. Same thing with something like this. The b to the -10th is in the denominator, so it would go to the top. Now there already was a 10 on the top, so when I move those b to the 10ths there, I multiply them together. And if I remove everything from the bottom, I replace it with a 1. So I could simplify as 10b to the 10th. So our last property for today is called the quotient of powers property. Quotient obviously means division. So this is saying if two of the same bases are being divided, we can subtract their exponents and keep the same base. So for example, if I had something like a to the m power divided by a to the n power, I could just keep that one that one base a, and just subtract the original exponents. So let's just see how that works right away. So like here, we notice that we have a base of y and a base of y. So if we're dividing the same base, our answer will have that base. So in this case, the base is y. And the way that we'd figure out the exponent is we'd take 4 and 3, and we'd subtract them. And we know that 4 minus 3 is just 1. Now, we could always use expanding to get our answer. So I would just want to check, why does that work? So here, if I had to write this out, y to the 4th, I'd write y times y times y times y. And on the denominator, if I had y to the 3rd, I'd write y times y times y. Now, if we have the same thing on the top of a fraction and the same thing on the bottom of a fraction, they can reduce. So this reduced to y, so we know we're correct. Let's look at this one here. So again, I can see that y is the base on top, and y is the base on the bottom. So if we're dividing those and they have the same base, our answer will have that base. And then to get the exponent, we'd take the current exponents and subtract them. Now notice when we subtract them, the order is numerator minus denominator. We have to keep that order. That's what it's trying to say by n minus m. So here we actually get a negative number, right? 6 minus 7 is -1. And that's why I've included this little note for you. If the difference of the exponents is negative, we will have to use our negative exponent rule. So 6 minus 7 is -1, but we don't want negative exponents because that tells us to do something. That was an action. So we'd take that base of y and move it to the denominator of a fraction and replace it with a 1 if we removed it. So we just have 1 over y. So again, I would like to show you that we could always solve these by expanding. So if I had to write this all out on top, I'd write y times itself 6 times. And on the bottom, I'd write y times itself 7 times. And then I'd start to cancel. So I'd cancel, 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 cancel. And if I cancel everything on the top, I replace it with a 1. And on the bottom, I'm just left with a y. And that brings me to one other way that you might want to interpret the quotient rule. Another great way to do that is to ask yourself, where are there more of that base? And after I canceled them out, how many more would be there? So let's try that method with this example. If I had x to the 19 on top and x to the 11 on the bottom, if I had to write this all out, I would write 19 x's on top and I'd write 11 on the bottom. So I can see that there's more on top. So after I cancel, like here, if there was more on top to begin with, all the ones on the bottom are canceled by all the ones on the top, but we're left with stuff on top. So if there was more x's on top of this fraction after we cancel, there would only be x's left on top. And how many would be left? Well, if there was 19 here and 11 there, there is 8 more on top, which means that there would be 8 left over that wouldn't cancel. So this would be x to the 8th power. Now again, that's just an alternate way of thinking about it. We could always go back to our quotient rule. If we notice that this base is the same as that base, we can take that base as our answer base, and then we'd take the exponents, right, 19 and 11, and we'd simply subtract those. And we all know that 19 minus 11 is 8. So whatever way you like is better. So we'll do this last one example here. So here I noticed that the base of -3 has an exponent and the base of -3 also has an exponent. So we have the same base. So the first thing I'm going to do is that new method I introduced, just asking myself, where are there more of that base? And if I cancel them out, how many more would be left over? So here, if I had to write this all out, there's more of that base of -3 on the bottom. I'd have to write it 30 times on the bottom and only 14 times on top. So I know that after I do all my canceling, there's going to be -3's left on the bottom, but there wouldn't be any left over on top. And then how many more would be there? Well, if there was 14 on top to cancel with 14 on the bottom, that means there would be 16 left over. And that's my final answer. Or again, we could be using the other way of the quotient rule, which is just recognizing that if we have the same base, each with an exponent being divided, the answer will have that base as well. So our base is -3. And then to get the final answer on the exponent, we would take the numerator's exponent and subtract the denominator's exponent. We have to do that order. So 14 minus 30. And we all know that 14 minus 30 is -16. But when we see a negative exponent, right, that was one of our rules of simplifying. We had to get rid of that. That negative exponent is in action. So currently the base of -3 is in the numerator. So the negative exponent would send it to the denominator and change it to a positive. And if we remove everything from the numerator, we replace it with a 1. So no matter what method we do, we get the same answer. So those are the 4 rules that we're starting with today for section 6.1.